Hi everyone, so I wanted to use this video to quickly talk about logistic regression. So logistic regression is a classification tool. I'll write that down. And its main goal is modeling the probability of belonging to one of those groups. And we're going to use this probability to decide whether or not we should put someone into one of these groups. So let's say, for our sake of argument, we have two groups, Group A and Group B. Right, so logistic regression is modeling the following quantity, right? So it's a probability that is a function of our data. And just to be clear, I'll write that out. So this is a probability. And it's working on our data. And what it returns is a score that is allowing us to decide whether or not we should put it in one of these groups. So we can think of it as the probability that we assign someone, let's say, to group A or B, given X. You kind of could interchange both of these, but let's just say it's the probability that we put someone into group A, given our data. So we'll make it, again, more explicit. This is the probability we put someone in group A, or we classify them in group A, given our data. Right, so the idea is if we can model this really well, then we can have a really good classification tool. Now, as we discussed in class, logistic regression, it's inspired by linear regression. But as we discussed, linear regression is not a good tool for classification. And to sort of see this, we're going to take an example. Let's say, for sake of an example, we were trying to diagnose someone based on some conditions. So let's just say our labels in this case, so we're trying to predict Y, and it is equal to 1. Let's say if you have an epileptic seizure. Right, so you're in the hospital and you want to know if someone's having a seizure or not, so you assign that to 1. And let's say it's 2 if you're having a drug overdose. Right, and distinguishing between both of these is very important. And so let's say your first instinct was to use a linear regression to classify people into group 1 or to group 2. There's a couple issues here. So the first issue, as we noticed in class, the first issue is that since linear regression it predicts a number, so since it predicts a number, there's sort of an assumed ordering that's going on here. So there's like an implied ordering. And this really doesn't exist, right? There's no reason for me to believe that, let's say, drug overdose is worse than an epileptic seizure, right? We really don't care, because I could have equally done the following construction. Instead of writing 1 as epileptic seizure, I could have wrote 1 as drug overdose. And then 2 as a seizure. Right? And these technically would both work, but the issue is if I were to look at both of these constructions, so let's call this construction 1 and construction 2, 1 and 2 might produce very different models. And that's quite bad. And then also, as I said above, by encoding one of these classes as a 1 and one of them as a 2, since linear regression thinks these are numbers, it sort of thinks incorrectly that in the second construction, it would think that a seizure is greater than drug overdose. And that doesn't make any sense. We're not trying to put that meaning here. This meaning here does not exist, right? That's not our point of classification. We're not ordering people together, right? We're just putting people into groups. Okay, so we now have two reasons to believe that linear regression is not a good tool for classification. All right, we discussed this more in class, so feel free to go back to that lecture and think about it a bit more. But we might believe that it's still a useful tool, and we might believe we can transform the linear regression. We believe we can transform the linear regression to fit classification needs. Right? And there's also one other issue with the linear regression that we noticed in class, and this is what we're going to heavily use when making this sort of transformation. We noticed, this is probably actually the most important thing we didn't like with linear regression, that linear regression produced probability estimates that were not valid. What does that mean? That means I got numbers like this. I got numbers like -1, maybe I got numbers like -0.5, maybe I got a number like 2, right? And these are not probabilities, right? To refresh your memory, a probability must always be between 0 and 1, right? That makes sense. I don't think I need to convince anyone of this. All right, so it must always be between 0 and 1. Okay, so how do we transform the linear regression to make sure that we always return valid probability estimates? Well, to do that, we're going to apply the logistic function, right? So remember, so we'll start with remembering what a linear regression looks like. So let's pretend that we were going to use the linear regression to predict these probability estimates. So this P of X, remember, this is just going to be the probability, let's say Y was equal to group A, given our data. Let's say I use a linear regression to model this probability. That means that it looks like this, right? So beta naught plus beta 1x, right? And I let software pick these weights here for me. So this is just picked by software. And also, I'll just make a note. Software gets these for me, right? But we still have this linear regression line. And we might want to transform this a little bit. And we want to transform this a little bit to get a probability estimate. So we're going to apply the logistic function. Right? And so what does that mean? That means instead of writing this line, I'm going to write e to that line divided by 1 plus e to that line. You know, this looks like a weird transformation, but actually it's quite intuitive, right? It sort of looks like our regression before because we have that same regression terms up here. But because I've taken e and then 1 plus e on the denominator, this is always, you can check this, between 0 and 1. And that's awesome, right? This is a probability estimate. So we're going to use this. We're going to use this as our logistic model. So when you click logistic regression in Radiant or in any other software, it is going to use this as its model, this entire thing. And that's awesome. And again, it can pick these betas, so these weights, the software will pick them for you and give you this function back. All right, so eventually when you get this function, predicting is very easy. So if you wanted to know the probability of, let's say 7, if your data was 7, you would just plug it back in, right? So this would be e, the beta naught plus beta 1 times 7, right? Because you have the model, it's going to give it to you. E to the beta naught plus beta 1. So, and again, you're not even going to have to type this out. Radiant will just say, give me 7. So give software You just give it x, and it returns the probability, right? And we use these probabilities to classify, right? And we'll talk later about how exactly we classify, but you can imagine what you could do is you can get all these probabilities, so probability 1, probability 2, probability 3, right? These are all your new observations. Let's say all the way up to probability 100. And then you can say, I will make a decision if p is greater than a half, right? And that makes sense, right? Because you might say something like, well, if my probability is greater than 50%, maybe I should put them in the group 2. So let's say your decision is classify into, let's say group A in this case, because we're sticking with A and B. Classify group A if any of my probabilities is greater than 50%. And that kind of makes sense, right? So if it's greater than 50%, we can move it. And this here, if you don't like 50%, you might have another reason to pick something different, and we'll talk about some other reasons. But this 50% can be changed. All right, maybe instead of 50%, you want 60%. Maybe you want 90%, right? We'll talk about the trade-offs behind choosing different boundaries. But that's it. That's really it. So if you were to do this in software, right? In software, all you'd have to do is decide to do the linear regression. So decide on logits. And then in Radiant, all you're going to do is pick what you want to predict. So pick your y, right? In this case, y, as we said in class, y could be whether or not you survived in the Titanic. And then you need to pick what x's you want to model. So pick your data. Pick your data x, right? And then Radiant is just going to return to you, or any software, in return, you get a model. All right, so you don't have to do any of this math above. You're going to get the model, and then your job is to decide if it's a good model or not. So you need to diagnose the model. You decide if it is a good model or not. Right, and we'll talk more about exactly how we do this, but one thing I'd like you to sort of look at is the validation set approach, which will be another video on. And this will help us decide if this is, let's say, a good model or not. So another thing, maybe like the confusion matrix would be another thing to look at. And that's about it. The only other thing I would say is if you wanted to interpret this, logistic regression doesn't have as nice of an interpretation as linear regression. But as I said in class, you can easily transform the logistic regression in the following way. So remember, we're modeling the probability of belonging to one of the groups in the following way. I'll write it out again. And, it's not quite clear, how does a change in x? So how does a change in x impact p of x? It's not quite clear. So we actually never really talk about having a change in x, how a change in x changes its probability. We instead talk about this transformation. So as I showed you in class, so I'll skip some of the details. We look at the log odds, so log p of x divided by 1 minus p of x. Because this is linear. Beta not plus beta x. So the interpretation here is the same as in linear regression. So you say a 1 unit change in x implies what a beta 1 change in log odds. It's not as clean. It's not as clean as linear regression, but we could still talk about changes in x in terms of the change in the log odds. And this is still kind of an intuitive quantity. It's just maybe not as nice as linear regression. But thank you very much, and I hope this was useful to you. Please let me know if there are any questions or things I can elaborate on for this section.